Okay. Cool. We're being recorded. Okay. Hi, everyone. Welcome to another week of GOCC. We're so glad to have Thiago Holleben tell us about simplicial complex and other things. Before we get started, I just want to remind us of the community statement. In short, it's that we're all learning, everyone has something to contribute, and no one has all the answers. Take it away, Thiago.
Okay, so first I'd like to thank the organizers. I heard about GOCC recently, and I've been coming to the ones this term, and I'm very happy to give a talk here. I'm going to talk about simplicial complexes arising from integer programs. So I'll talk about a little bit about kind of like the motivation and the origin of the problem, but it's a problem that comes from commutative algebra, and it ends up having like many nice connections to combinatorics to the point where, like, to me, it's more combinatorics than algebra even. This is joint work with Trung Chau, who was a PhD student but just finished, Art Duval, Sara Faridi, my advisor, Susan Morey, and Liana Şega. So this is like a picture of the group. From like left to right, that's me, Art, Susan, Liana, Sarah, and then Trung. This is where the project started. It was in a workshop in Banff, in Canada. And it's like an amazing place. If you look at the pictures, I don't know if you've ever seen it, but like it looks like it's AI generated. It's so nice. Okay, so like a brief outline of what I'll be talking about. So I'll start by trying to motivate the problem, and that will actually be like a big part of the talk. The actual motivation for this problem is not going to be the one I'm going to talk about. I'm going to kind of like motivate the problem from kind of like F and H vectors of simplicial complexes, but that's not where people kind of like why people started studying this. Then I'll talk a little bit about the history of the problem, of like what is known and things like that. Then the connection with integer programming. So it will take like a little bit for the integer programs to show up. And then finally, I'll talk about our results. Okay. So like the first thing that we need, that will be kind of like the main object of anything that I'll be talking about today, is the definition of a simplicial complex. So a simplicial complex on a vertex set V is going to be basically a collection of subsets of this like vertex set, such that if you have a subset of something in this collection, this subset also has to be there. Okay. And we usually depict like the simplicial complexes with like a picture like this. So in this case, the sets in the collection would be 1, 2, 3, 2, 3, 4, 2, 4, 5, and 5, 4, 6. They're called the faces of the simplicial complex. And one thing that we'll meet kind of like many times throughout the talk is this like generating function for the number of faces, right? So you have a collection, and then you can look at the generating function of the number of sets of size 0, number of sets of size 1, and so on. So it's like a number of faces of each size. There's like a little shift on the size and the index, but that's okay. And one thing that I didn't write here, but we'll also need, is the definition of an induced subcomplex. So I guess I can write it here. So an induced subcomplex is going to be, I'll give an example. It's maybe more like easier. So let's say the induced subcomplex, it's always on a subset of the vertices. So let's say I want to look at the induced subcomplex on 1, 3, 4. Then what I'm going to do is I'm going to basically take every face that contains 1, 3, 4, but nothing else. Okay, so in this case, I have the vertex 1, I have the vertex 3, and I have the vertex 4. And then I have this edge and this edge. Okay, so this would be the induced subcomplex on 1, 3, 4. There are like a little bit of like technicalities depending on whether you assume that every vertex is a face or not. For the purpose of this talk, let's just assume that every vertex is a face. But yeah. So there's two ways to represent a simplicial complex. The one that I just showed you is kind of like by the maximal faces, which are called the facets. And there's another way to represent a simplicial complex, which is instead of saying the maximal things in the collection, you tell me the minimal things not in the collection, right? So these would be the minimal non-faces. And given the minimal non-faces of a simplicial complex, let's say we have the vertex set being like the interval from 1 through n, then we can define an ideal in a polynomial ring that's called the Stanley-Reisner ideal. Okay, so this ideal, it's going to be generated. So the way we do it is we look at every subset that is not in our simplicial complex, so the non-faces, and we turn them into like monomials. So like a subset, you take the product of the variables in this subset, and you look at the ideal generated by them. So in other words, it's like the ideal generated by the minimal non-faces of your simplicial complex. Okay, this is like very useful when you're going to study simplicial complexes, simplicial polytopes, and things like that. Okay, and it's like a very nice connection with commutative algebra. Okay, so in combinatorial topology, like one of the things that people do like all the time is you have a simplicial complex and you want to study the homology of this complex. So you want to study like, oh, does my complex, my simplicial complex have poles? Is it connected? How well connected is it? And that information is usually like displayed, let's say, in like the homology of the simplicial complex. But for this talk, what we care about is like a finer thing, where instead of looking at the homology of the complex, we want to look at the homology of every induced subcomplex of the complex that we have. Okay? And the sequence that I'm going to talk about, this is kind of like the actual main object, is called the betti sequence. The betti sequence is usually associated to the Stanley-Reisner ideal. But for us, we can just kind of like abuse notation a little bit. And I'm going to associate the sequence to the simplicial complex. So I'm going to write B beta delta for the betti sequence. And it's defined like this. So we're going to look at the dimension of some homology with like a weird index. We won't really need to come back to this index very much, but just keep in mind that it's like a weird shift. And it's a sum ranging over every induced subcomplex. Okay. Now, one thing that it's not too hard to prove, but like I won't do it here because I don't think it's necessary, is that from this definition, beta 1 is actually going to be the number of like hollow simplices that your simplicial complex contains. So a hollow simplex would be something like, let's say, a hollow triangle is when you have the 3 edges of the triangle, but you don't have the actual triangle there. Okay, a hollow tetrahedra would be the same thing. You have all the faces except for kind of like the whole thing. And beta 1 counts exactly that sort of thing. Okay, and the definition is like a little bit technical, but really the idea is what we need. We won't kind of like do any sort of, well, I guess we'll do one example, but then we won't do any computation with it. And the idea of this sequence is that it's a way of organizing the homology of every induced subcomplex at once. So if I want to talk about the homology of the complex, I have like numbers, like the dimensions of the homologies. But if I want to talk about every induced subcomplex at once, then this is the way kind of like people, one of the ways, I guess, people figured out on how to do it. Okay, so I want to do an example. So I want to compute the sequence for a pentagon. And for that, what we need, like in case you've never seen homology, these are like the 3 interpretations of homology that we need to compute it for a pentagon. So the -1 homology is only going to be non-zero, like the dimension, if it's 1, so it's either 0 or 1, and it's only going to be 1 if we have like a simplicial complex that doesn't have any vertex. Okay. The dimension of the H0, so of the 0-dimensional homology, is going to be the number of connected components -1 of the simplicial complex that we have. And the first homology is going to be the number of hollow cycles. Okay. Now, I want to do it for a pentagon. So if you have a pentagon, first of all, let me, I guess, put it in green. The actual pentagon is what you get if you choose the whole complex, right? And this has one homology. So dim H1 of, let me draw a little pentagon. is equal to 1. Put the real numbers there. Is equal to 1. Okay? And this is what we get. Oh, no. And this is what we get when we pick the whole thing. Now, if you want to look at every induced subcomplex, you basically need to pick a subset of the vertices. And then you need to check, okay, does this have homology or not? If you take a subcomplex and it doesn't have homology, it won't contribute to the sequence, so we don't really need to look at it, right? So if you take, for example, 2 points, I'll draw it here. If you take these 2 points to define your induced subcomplex, you would have something like this. And this X doesn't have homology, so it won't contribute. If you want to have 2 vertices contributing to the sequence, you need to pick 2 vertices that are not adjacent, like this. Okay? And when you do that, the picture that you get is exactly this one. Because it's like you pick 2 vertices and they don't have to be adjacent. There's 5 ways we can pick a pair of vertices in a pentagon such that they're not adjacent. Okay? And for this one, let's say we want to pick more than 2 vertices. Let's say now we want to look at the subsets of 3 vertices. If you pick 3 vertices in the pentagon, let's say I pick this, this, and this, then the complex that you have is going to be basically like 2 edges glued together, which if you look under like these 3 bullet points that I have there, you'll see that, again, this does not have homology, so it won't contribute to the sequence. So we don't need to look at these ones. And then if you want to pick 3 vertices, it turns out that the only thing that can happen is you pick a vertex, you pick something like this. So you pick 2 vertices that form an edge, and then one that is kind of like in a different connected component. Okay, and then the picture that you get is exactly this one in the middle. And again, it turns out that there's 5 ways to do this. 5 ways to pick like 3 vertices like this. And then now when we want to see what the sequence is, the sequence always starts with a 1. The sequence always starts with a 1. So it will be something like 1 because of the empty side. When you don't pick anything, you get the empty side, and so it's always going to start with a 1. Then let's look at the subsets of size 2. So it would be like these ones. So we have the number of vertices. The equation to find the index is something like this. The shift that we have is something like this on the sequence. So when we have 2 vertices, we're going to have 0 homology because it's like 2 different connected components. So we put a 0 on the other side. And now this number of vertices is equal to 2. So I guess I can erase that. And then so for I, you get that I is equal to 1. Okay. So the sequence will be something like 1, 5. If you do the same thing for the picture in the middle, it would be number of vertices, which is now 3, minus I, minus 1 is equal to, again, 0 because you have connected components. So now I is equal to 2. Okay. So since we also have 5 ways of doing that, we get a 5. And then I won't do it, but for the pentagon, you get a 1 on I equal to 2. Okay. So the sequence that we have is 1, 5, 5, 1 for the pentagon. And there's like, I mean, if you've never seen this, and this is the first example that you see, there's like many questions that you can ask, right? Like, this is symmetric, this is unimodal, this is well concave. There's like all sorts of questions that you can ask. And the thing that I want to point out, this is not related to the problem itself, but it's like a nice motivation for studying this sequence. So like, why should we care about this? I just realized that this is in the front. Okay. Okay. But like, why should we care about this sequence? And one thing that was showed like a long time ago by Stanley is that if you take your simplicial complex to be a triangulation of a sphere, your sequence, like this betti sequence, is going to be symmetric. So we just did it for a pentagon, which is a triangulation of a circle, right? And the sequence we got is 1, 5, 5, 1, which is symmetric. Okay, so this is kind of like, to me, this is like a very nice theorem relating this sequence, which is like about homology. So like the combinatorics of the simplicial complex. Okay. Now, two other things that I won't really go too much into it, like for my talk, but if people are interested, we can talk about it. Is that this sequence can be used to compute F and H vectors of simplicial complexes, and it has connections to many problems in combinatorial topology, like the Ray numbers and Halley-type theorems. So again, I won't go too much into these, but if people are curious, we can talk about it at the end.
Yeah, small. Just could you show quickly how the pentagon is a triangulation of a sphere?
Okay, so yeah, I guess I can write it here. So okay, I guess I see what the problem is. When I say sphere, I mean like any dimensional sphere.
Okay.
Yeah, I'm sorry, dimensional sphere. So in particular, I'm calling the circle a sphere, which yeah, it's common, but it's like a one sphere. Okay, so it's more like a D sphere. Yeah, I'm sorry.
No, okay.
Okay, and then okay, and now so kind of like the reason I'm talking about this and like I mentioned spheres and things like that is because I wanted to talk about the upper bound theorem, or at least like a version of it, because it's what kind of like motivates the problem in a nice way. So one question that you can ask, if you like, let's say polytopes, is which simplicial polytope, if it exists, so it's not clear that it exists, but if it exists, which simplicial polytope maximizes the F factors of simplicial polytope? So in other words, fix the dimension and the number of vertices. Okay? Can we describe a d-dimensional polytope, which I'm denoting here by PD, with n vertices, so that the F vector of any other simplicial polytope with like the same parameters, so the same dimension and the same number of vertices, the entries on the F vector is at most the entries on the F vector of this like PD. So a version of this question, I think it's like slightly more general, or maybe, yeah, I guess it's a lot more general. Was asked by Klee in 64, and then Stanley proved it in 75. So there is like a simplicial complex, simplicial polytope with this property. And the sort of thing that you can ask is, okay, is there a version of this for this betti sequence that I'm defining, right? So is there a simplicial complex that maximizes betti sequence? So in other words, we need like parameters, right? Because just like for how polytopes, you can always, I don't know, add more vertices and make it bigger by doing a little subdivisions or something like that. There's similar operations that you would be able to do to simply increase every entry. So what we do is we fix one entry of the betti sequence. We fix the first, let's say, non-trivial entry, which is the beta 1. When you fix beta 1, the question is there a simplicial complex delta Q such that for any gamma with beta 1 of gamma equal to Q, every entry on the betti sequence is bounded above by the betti sequence of delta Q. Now, this is, again, this is not how the people in commutative algebra were studying this, but one version of the statement, like a special version of the statement of Taylor's thesis from 66, is that the answer to this question is a yes. So in her thesis, this is where kind of like this whole field started, like doing the kind of like more combinatorial side of it. What she showed, I guess one version of what she showed, is the betti sequence of the d-dimensional cross polytope. So that's like the cross polytope. The cross polytope has minimal the minimal non-faces of the cross polytope are disjoint edges. Disjoint edges. So like it's like a square, the minimal non-faces are like the diagonals, or you do something like an octahedron. I don't know how to draw it nicely here. Something like this. Here. the minimal non-faces there. I guess it gets harder to see, but the minimal non-faces would be 3 edges, and then there's like one version of this for every dimension. And what she proved is that the Betti sequence for the cross polytope are the binomial coefficients on like a specific like number of the d plus one, sorry, d plus one choose I. And what she also showed is that if you take any complex where the beta 1 is equal to d plus 1, that sequence is going to be bounded above by the binomial coefficients. And the way I want to think of this, like from now on, is I want to think of this as number of I minus 1 faces of the simplex, let's say of a simplex. Okay. So we'll come back to this, but in some sense, what's like implicit in what she did, like from this perspective, is that the Betti sequence is bounded above by the F factor of a simplicial complex. Okay. Now, to actually state the problem, we need like a less definition, which is going to be the definitions of the powers of an ideal. So this is where kind of like the algebra comes in for the motivation of the problem. And the idea is, let's say you have a simplicial complex. From a simplicial complex, you can get the Stanley-Reisner ideal. From the Stanley-Reisner ideal, you can look at the powers of this ideal. So the powers, let's say the rth power is going to be, you look at every generator and you look at products of these generators. If you're looking at the second power, you look at the products of every tuple of generators where you are allowed to repeat it. So if you're looking at the second power and you have 2 generators, you would have like, if it's F1 and F2, like if it's F1 and F2, your power would be F1 squared generated by F1 times F2 and F2 squared. These would be the generators of your ideal. Okay, you just look at every possible product containing 2 elements of the generators. And then once you have this ideal, this is like power, what you can do is, okay, you start from an ideal where the generators, they don't repeat variables, right? So it's going to be something like x1 times x2, but it's never going to have x1 squared. So what we do is we replace the x1 squared by x1 times a new variable. Okay, so we're going to basically remove the squares of the monomials, or like the cubes, and we want to make it like square free. So I have an example of this. So let's say you have the Stanley-Reisner ideal of delta this complex here, which is like the simplest example that I could think that's not trivial, but we'll see that things get complicated very quickly. So the second power, as I said, it's going to be the first generator squared, the first generator times the second generator. So we have like the x1 squared x3, x2 x3, and then the second generator squared. Okay, that's the second power. What I want to do next is I want to replace the repeated variables by new ones. So I have like x1 squared here. Every time x1 squared appears, I'm going to replace it by x1 times x4. So x1 times x4, here I have x1 times x4, and here I have x1 times x4. Okay. Another repeated variable that I had was x2 squared. Every time x2 squared appears, I'm going to replace it by x2 times x5. It only appears once, so that's it. And the third one is x3 squared. Every time it appears, I'm going to replace it by x3 times x6. This is called polarization. And the point is, now that we again have an ideal that is generated by these like square free monomials, they don't have like repeated variables. It turns out that you can associate to this ideal another simplicial complex. So the simplicial complex delta R that I was defining previously. So here it's delta 2. It's going to be the, let's say, the Stanley-Reisner complex of this ideal. So in this case, the facets, so the maximal faces of this complex would be 1, 4, 5, 6, 1, 2, 4, 6, and so on. And the minimal non-faces would be 1, 4, 5, 1, 4, 2, 5, 1, 4, 2, 3, and 1, 4, 3, 6. Okay, So we start from a simplicial complex. We do this like algebraic operation, and we get a new one, which I'm going to denote by this kind of like power notation. Okay. So in this case, it's a second power. But you can see that, I mean, I started from basically the simplest example that I could, and I already got something that like I can't even draw because it's like 4-dimensional, 6 vertices, and things get very complicated very quickly. Okay. So now kind of like moving on a little bit to the history of what's known. About 50 years after Taylor's result in her thesis, this group of people, so Susan Cooper, Sabine El-Khoury, Sara Faridi, Sarah Mayatang, Susan Morey, Liana Şega, and Sandra Spiroff, they started this project it was like a Women in Commutative Algebra conference, and they started like a systematic study of sequences of complexes arising from this procedure. So you start from a complex, you take this power procedure, and then you want to study the betti sequence of these complexes. Now, people had looked at this before, but they had kind of like a very specific way they wanted to look at it, and it was like very systematic. And that point of view, I think, started in that conference. And then they wrote like a bunch of papers. And one paper from like a couple of years later, it's like very recent, I think it was published this year even, is if you have an integer q, and it's from a subgroup of the original people, if you have an integer q, then there exists a simplicial complex gamma q. This is the notation I'm going to use, gamma q, such that the beta 1 of gamma q is equal to q. And when you look at the powers of gamma q, it maximizes betti sequence. Okay, so whenever you have a delta where the first entry is q, this gamma q is going to maximize the betti sequence. Okay, and they gave a description of what gamma is. Okay, but what they didn't do, it was left as like a conjecture, is what is the betti sequence of gamma? They proved that it was an upper bound, but we didn't know what the numbers were, and we still kind of don't know. So the conjecture that they had was that the betti sequence of any power of gamma is the f factor of a simplicial complex. But the way I stated it sounds like they didn't know what the complex was, but they actually kind of like, they thought, oh, we think this is the betti sequence is the f factor of this complex, and then they made the conjecture. So they had a complex in mind of what it should be, this SRQ, which I'm going to define in a couple of slides. But the point is, we get to the same situation from Taylor, where the betti sequence of a simplicial complex, like an arbitrary simplicial complex, is bounded by the number of faces of a simplex. And then when you do this power procedure, the idea, it's a conjecture, the idea is that it's going to again be bounded, the betti sequence of the powers, by the f factor of a complex. And the question is, okay, what is this complex? So this complex is called the scarf complex, just in case I mention it. Yeah, and the definition of that complex is where the integer programs come up. So what they showed, this is kind of like a mixture of a theorem and a definition. I'm stating it as a definition, but in their paper it's like a theorem. What they showed is, okay, let's say you have this set of vectors, which is the vectors with integer coordinates, where the sum of the entries, so this is my notation for sum of the entries, is equal to r. Okay? What they showed is that there's a simplicial complex, which I'm going to denote by SRQ. So again, this is kind of the way I'm saying it, it's more of a definition. But the definition of like the simplicial complex is, okay, so the set of vertices is like you can think of it as like the compositions of R with Q parts that can be 0. And a collection of vertices is a face if and only if, one, every subset is a proper subset. So you want it to be a simplicial complex. So it's the definition is kind of a little bit recursive. And the second thing that you want, and this is where the integer programs come in, is you have a system of integer programs, sorry, and you want the only solutions of this set of integer programs to be the vertices in your set. So the system of inequalities, like the integer programs that we have, are going to be basically, you take your W which let's say you want to know if it's a solution or not, and you take the dot product with these like EA vectors. So the EA vector is going to be like, it has ones on the coordinates in A and zeros outside. And so you take it, so it's basically, you want to look at every possible subset of Q. You take the sum of the entries in that subset of your vector, and you want it to be less than what you get when you do it for the vertices of what you think is a face. Okay? So one thing is, this is horrible to compute. It's like very, very complicated to do it, like even in a computer. We can only do it for very small examples because in whatever way you want to think about this, something's exponential and something's like horribly exponential. Because when we say for all subsets of 1 through Q, that's like exponentially many. So that's like exponentially many things that you're going to have to check here. And then you also want to know like what are all the faces, right? So you want to check it for every subcomplex, for every subset. Do you have a question? I see that.
Yes. So can you remind me of what this NRQ is? So it's
it's here. It's like every vector that has natural coordinates, and the sum adds up to R.
Okay.
So those are
Great.
Okay. So those are the vertices of the simplicial complex.
Yes.
And if you want to know what's a face, what you do is you look at this side of all of these like inequalities, and you want to know that you don't have any extra solution. You only have the ones that that you fixed before, like these AIs. Okay, so I can do an example. I'll do an example of a face and of a non-face. So first of all, if we want to do an example of a face, what we can do is we can take this like pair of vectors, for example, let's say 1, 1, 0 and 0, 1, 1. Those are two vertices, and we want to know whether this set is an edge. So since we're talking about edges, the first condition that we had, which was like the recursive one of like every proper subset is a face, it becomes kind of trivial because like the proper subset is only one vertex or no vertex. So we don't have to worry too much about that. But we do have to worry about the second one. So these are all the inequalities that we have. So when you take the dot product with the vector 1, 0, 0, you get 1, 0, 1, 0, you also get 1. So on this side, just to remind you, on this side, we have kind of like the max of the dot products with these two vectors, right? So when you take the dot product of 1, 0, 0 with these two vectors, the max is 1. When you take this one, 0, 0, 1, like this one here, the max will be 1 because of the second vector, okay? And for some entries, you get 2. For most of them, you get 1s. And if you look at the system, this one is not really hard to prove. The only solutions are actually 1, 1, 0 and 0, 1, 1. If you want to see kind of like why would that be the case, is well.
Yeah. So the only solutions in natural numbers are the only solutions
in natural numbers adding up to R, like the only solutions where you also want this. So 1, 1, 1 is equal to 2. So you want natural numbers, and you want the dot product with like the sum of all coordinates to be 2. Okay. So if you want to know kind of like why is that the case, the first 3 inequalities here that we have, they basically say the maximal values of each entry of the vector, right? Because it's like, okay, the first entry of W has to be at most 1, the second has to be at most 1, and the third has to be at most 1. So the vector only has 1s and 0s. But when you look at the first restriction that we have as well, this one that I wrote, you see that the only missing vector that could be a solution in that case is the vector 1, 0, 1, which is like the other vector that has 3 coordinates, 3 natural coordinates, and it adds up to 2. And that wouldn't work because of this vector, because of this inequality. So when we look at the inequality, where basically we take the dot product with itself, it had to be at most 1, but we would get 2. So in this case, it's not a solution, and so it is a phase. Now let's do an example where we don't have a phase. So now we're going to do the vector 2, 0, 0, and the vector 0, 1, 1. And this is what we have. So it's like the similar inequalities, but the ones in red are the different ones. So like this and this. And notice that the problem for the previous one now changed. Now instead of being 1, now it became 2. And so, oh, this 1, 1, 0 is a typo. This should be 1, 0, 1. So the vector that the only vector that could be a solution before and wasn't now is. Okay. So since we have an extra solution, it means we don't have a phase. So this pair here is not a phase of S2, 3. Okay. Now, in terms of kind of like what is known, what ends up being the case is that we only know answers, basically any answer, when either R or Q are low. And in some cases, they have to be very low. So for example, one thing that they showed when they made the conjecture, it's the same group of people, is that if R is equal to 2, so I have two conditions. If either R is equal to 2 or Q is less than 5, then their conjecture is true. So if you take any simplicial complex, beta 1, with beta 1 equal to Q, then when you look at the Rth power, the betti sequence is going to be bounded above by the power of gamma Q, and the betti sequence of gamma is equal to the number of faces of this like weird complex defined using the integer programs. Okay, so it's like very specific conditions, and it's kind of because the problem gets really hard very fast. So I think now I have pictures of like what do these complexes look like, and they are very like they don't tell the whole picture. So on small cases, it turns out that the complexes are actually famous constructions that people know from like, I don't know, subdivisions operations. So this is a picture of S23. The vertices are like the compositions with at most 3 parts. And it's like very nice. It's basically you have a triangle and you subdivide it very nicely. It's a very nice complex. I think I have a picture of S34. It's again very nice. Like from here, I guess you could guess. So S2, 3 is equal to like you take a triangle and you subdivide it like this. S4, 3, you subdivide it like this. So you can kind of guess what the answer would be if you had like SR3. But that's kind of where things stop being nice. So I'll first mention the result that we have. And I guess now I'll move more into the results. And I think I have pictures in the end of the ugly things that happen when you increase the R and Q. So this is the main result. So that's like Chau, Duval, Faridi, myself, Morey, and Şega. So if you let Q be an integer, then for any simplicial complex with like the same assumption that we have all the time, the third power, so the third power of this complex is going to be bounded above by this. This was known. But then we proved this equality here. So we proved that the betti sequence of gamma 3q is equal to the number of I-1 faces of S3q. And one thing that we can show, so it's like the methods we use, they work in higher powers. They just don't kind of like solve the problem, but they do give you many faces of this complex. So what we show is that this complex is not flagged. So one thing that happens in S, I can go back to the pictures. So one thing that happens here is whenever you have 3 vertices adjacent to each other, like whenever you have a triangle, the triangle is filled, right? So when that happens for like all dimensions, it means your complex is what people call a flag complex. And it was kind of a surprise that basically for any case that was not known before, the complex is not flagged. And this idea, the idea that the complex is not flagged is that basically when you increase R, especially when you increase R, things get more complicated to the point where like we don't really have much intuition to what happens when R is like, let's say, more than 5. And the methods from, just like a comment, the methods from R equal to 2, they generalize a little bit, but they don't solve the problem. There's like a lot left to do to R equal to 3. And the main point is that when you vary R and Q, the complexes, they look really, really different, except when Q is like 1, 2, or 3. In that cases, then they look alike, but then other than that, it's very different. So here's like a comparison, a nice graph of a comparison of the bounds that people had of like what can the largest betti sequence of a third power be. So I don't know if you can see it. Hopefully you can. This one here, the largest one, was the bound that people get from the work of Taylor, the one that I mentioned in the like the middle of the talk. This one here, the green one, is the one that people get from the work of this other group that started looking at this from this more systematic way. So like El-Khoury, Faridi, I don't remember the subset, El-Khoury, Faridi, Şega, and Spirov. So this picture is an exponential scale. So the improvement is actually kind of like massive. So you go from like trillions to like 5,000. The improvement is like massive. The maximal entry here is around 10 to the 5. This is for Q equal to 6. The maximal entry is 10 to the 5. And the maximal entry before was 10 to the 15. So the improvement is like massive. And our result is sharp. So like you can't do better than it. There exists a complex that achieves it. Okay. Yeah, that's the pretty picture. And one question that you can ask is kind of like, okay, why is the case R equal to 2 and R equal to 3 so different? Okay. And before that, I want to show you a picture of S2,5 and S3,5. So I won't show you a picture for the 2,5 because it's like the dimension is very high. But the idea is there's two types of facets. So the first facet is basically you look at the vector 1, 1, 0, 0, 0. You take a permutation of 5 elements and you permute this. That's going to give you like a set. That set is a facet. Okay. The other one is you take this set. So it's 2, 0, 0, 0, 0. And basically the vectors that only have ones and start with a 1. So this one has 1 here, 1 here, 1 here, and 1 here. Okay. And then you do the same procedure. You pick a permutation of 5 elements and you apply the same permutation to all the elements in this set. That's going to give you all the facets of the second type. So this set here is one actual facet, but when you apply permutation, you get other ones. And it turns out this is a result of this other group that I mentioned, that these are all the facets. Okay, so the picture that we should have is that, okay, there's a blob in the middle, which are the vectors that only have ones. And then you have these like pointy things pointing out, which are these things where kind of like the pointy thing here is a vector starting with a 2. This one would be like 0, 2. This one would be, I don't know, like 0, 0, 2, and so on. This is the picture of the complex, okay? And now here's a picture of the edges. I won't draw everything, but of the edges for S3Q. So now the third power. And again, it looks like there is a blob here, right? There's like a big blob in the middle and the pointy things. But that's not the actual structure of the complex, which is kind of the problem. What is actually happening here is you have a blob. I don't know if you can see it. There's a blob in the middle, like in the very center. And then there's a bigger blob, like not a blob, but like a ring of things, right? These vertices here. And then you have the pointy things. So there's in some sense one extra layer, okay? And why is that the case? So when R is equal to 2, there's two types of vertices. You either have a vertex that only has 1, 1, zeros, or you have a vertex that is 2 and zeros. And that's because you have two partitions of 2. When R is equal to 3, things get more complicated. So now we have three types of vertices. We have the 1, 1, 1 vectors, we have the 2, 1 vectors, and we have the 3, 0 vectors. each one, it's like, again, it's because of the number of partitions that we have. If we go back to the picture, the things in the middle, I don't know if you can actually see, but like these things here, they are the 1, 1, 1 vectors. The things to the side, like the ones in this like ring, they are the 2, 1 vectors. And the ones on the actual, kind of like the actual pointy ones, they are the 3, 0 vectors. Okay, so the complex, it's kind of like taking the partitions into account when, for some reason, it's kind of a mystery, we don't really know why, but the partitions, they kind of show up in the structure. And the thing is, if you take the partition 1, 1, 1, and 1, so if you take vectors that are of the form like 1, 1, 1, 1, 1, and zeros, we know what they are adjacent to, like in terms of edges and even higher faces. We have a very good idea of, well, like, which faces are they in and which faces are they not in? And the answer is they're basically in everything. The other extreme would be the partition where you only have one part. So that's like the vector R zeros, right? And in that case, that vector is connected to almost nothing. So that's where you get the pointy thing in the end. It's because it's not connected to anything. And so when you draw it, it looks like a pointy thing because you have a vertex that's almost isolated. And what happens is when R is equal to 2, these are the only 2 partitions. So in some sense, this is why we have all of these kind of like nice results about like many things. So their results for R equal to 2, they were able to generalize it to basically nicer things, to any power, to get like upper bounds for any power. And the idea is because you only have 2 types of partitions. When you increase R, you have more types of partitions. And basically, the more types of partitions, the more complicated the situation is. Okay, because you have to basically test more things. Now, this is, I wanted to kind of like mention this, just so kind of like, I mentioned on the abstract, I was going to talk about the phase structure. So I'm going to talk about this theorem, which is like a list of the minimal non-faces. If people are curious, I can describe the facets, like the maximal faces as well. But it's kind of like, I would say it's less intuitive of what's going on. Like it doesn't kind of, I wouldn't say it tells the story. But this is kind of a very important part of the proof. So up to permutation, and when I mean permutation, I mean like kind of permuting the coordinates, not the vectors. So up to permuting the entries and adding extra zeros, the minimal non-faces of S3Q are, so we have this triangle. This is what implies the complex is not flag, because you have like a hollow triangle. These 3 things are adjacent to each other, but the actual triangle is not in the complex. Vectors like this, so if you take like 2, 1, and then 2, 1, but with separate coordinates. If you have 2, 1, but they share the 1 coordinate, that's also not a face. If you have 2, 1, but they share 1 coordinate, that's not kind of like the 1. So here the 2's have different coordinates, but they still share a coordinate. So it's like the 2 of one vector is in the coordinates of the 1 of the other vector. This is also not a face. And if you take 3, 0, and you try to make it adjacent to anything that doesn't start with a 2, it won't work. Okay, so this is like a complete list of the minimal non-faces. If you actually kind of try to write everything, it becomes 10 minimal non-faces. But that's the complete list. For the facets, there's 5 types of facets, but their description is less clear. And I think I have one more thing that, well, I guess 2 more things that I wanted to point out. So if you want to try higher than 3, like what happens? We have pictures for the edges, not for the whole complex, because for the whole complex, it's like insanely costly to compute. But for the edges, we can actually do it. We know all the edges up to like R equal to 8 or something. And like we could do more. And the structure of the complex seems to capture, if people are familiar with like the orderings on partitions and things like that, when you write it and you think of it as like a polar coordinates, let's say, the thing in the middle is the 1, 1, 1, 1, 1 partition. then there's like a circle of vertices. That's the 2, 1, 1, and then 2, 2, and then 3, 1, and then 4, which in this case, you might recognize as the domination ordering for partitions. But then the really sad thing is this is not completely true when you keep increasing the R. So like for R equal to 6, I think, which I guess it's also when the domination ordering starts to have problems with the partitions. For R, I think it's like 6 or 5. You don't get like a 100% kind of like pretty picture like this, but you still have very nice things going on, and we don't know what it is. So like if people are interested in this is like one thing that you can look. There's like more things. Again, if people are interested, we can talk more about the other stuff. And just before I finish, this is like the end of my slides. I just wanted to point out that I focus on like one part of the proof. There's a whole other part of the proof where, so I focused on what is the complex, right? So where's the theorem? So I focused on what is this complex, S3Q. But to actually prove the equality, you need to use other methods. So to prove the equality, the method is basically like discrete Morse theory, if anyone likes that. And it's also very combinatorial, like very topological. And it's kind of a completely different set of techniques. So it's like very nice. If people are interested in this, there's like many things that you can do. All of this is like very recent. It's from like last year or something like that. So yeah, that's it.
Thank you so much, Thiago. That's a really fun result. That's, yeah. I had some questions, but you answered them with the talk. So if anyone has questions, feel free to just unmute or type in the chat.
So I have a question, but it's not really a mathematical question.
Okay. Okay.
Tell me what you know about Diane Taylor.
Not much. So what I know about Taylor, I talked to my supervisor about this at some point, and what I know is that like she did her PhD and then I think she left academia, and I think later on someone told her, I don't know what. I can ask my supervisor again because I forgot the story, but someone told her that like her result is now being used like all the time. So her thesis was like cited all the time in comparative algebra, and she didn't know about it. I think. Yeah. This is all that I know. Yeah, that she left academia and yeah.
Wow.
Okay.
I'm wondering, oh, no, did you go ahead? I had a non-mathematical question. So I'm wondering what you use for the computations and for the pictures. I feel like those are, the pictures are very hard to get, I imagine.
Yeah. That's a good question. So these ones, I wasn't the one that made them. These are like basically just on the preprints that we're writing. And I think they're also in other papers as well. So this is using text, but I wasn't the one to write them. I just kind of like copied and pasted the thing from like the code from our preprint.
Yeah.
And this one, which is the one that this one.
Oh,
yeah. So
sorry.
So this one, okay, every other picture is using Python.
Okay, yeah.
So the data is generated. This one is like completely Python. This one and the other one is preview. So this one. So this one, I generated the data using Macaulay 2, I think.
Yeah.
Because again, so if you actually go through like how are the proofs of the statements and things like that, many of the proofs are very algebraic. Like they use many kind of like algebraic things. So Macaulay's better to do that. If you like the geometric thing, you can also do it on Sage. The program that we have to compute edges uses Sage. And then you use Python. There's like packages for graphs.
Yeah.
And then you have like a list of edges, and then you just try to make it prettier. Yeah.
Yeah, I'm very impressed by this being done in Sage. I feel like, I don't know, when I've made images using it, they're nowhere near this good. This is
So
great.
one like nice kind of like fun fact about the fact that this was done in state is that, okay, you have like, I don't know, 50 vertices or something. And I wasn't like, okay, put this vertex in this spot, put this vertex in this spot, put this vertex in this spot. So if you've ever done like anything graph theory related with Sage, you probably know that like when you try to plot it, Sage has like an algorithm using, I think it's like spectral graph theory, to find where are the best places to put the vertices, considering the edges that you're giving it, right?
Mhm.
And so the fact that we get this kind of like layered structure from that, it's kind of like, okay, there really is something there, right? It's,
Yeah.
it wasn't like cherry picked. It's really what you
Yeah.
get.
Yeah. Oh, yeah. And then also, so we know this bound on the Betti numbers. And the Betti numbers calculate things about homology and cohomology. What
Uh-huh.
is it? I mean, what does it mean for the homology and cohomology groups? Okay, so you have this boundary. I guess my question is, what does it mean in terms of
The bounds.
homology? Yeah.
Um,
It's a vague question. It's okay if that's
No, but it's a good question because so one thing that's kind of like implicit in everything that I was saying is if you go back to the upper bound types of results, so like the upper bound theorem and the question that we have for this setting, where is it?
Mhm.
So when we talk about here, yeah. So when we talk about the upper bound theorem, you have two parameters that you need to fix. You need to fix the number of vertices, and you need to fix the dimension of the polytope for like whatever thing you're trying to prove an upper bound type theorem for. When we talk about these betti sequences, we don't fix anything. We really only fix the first entry on the betti sequence, which you can prove. It's not hard to prove, but like you need like an argument that this first number is the number of minimal generators of the Stanley-Reisner ideal. So in some sense, what this is saying is that it doesn't matter if you keep adding vertices. If you don't add new minimal non-faces, you can't increase it as much as you want, which is not really intuitive if you think about it, right? Because when we talk about, let's say, F factors, you add a vertex and you get more faces. But in this case, it's somehow saying that, okay, the minimal non-faces are telling you how much homology can the induced subcomplexes have. So I think that's kind of maybe vague, but yeah.
No, but that's very cool. Wow.
Okay.
Yeah. That's great.
Yeah.
Anyone else? Aditya, did you want to?
Yeah. So the picture that you had, that's like one of the craziest interpretations of the dominance ordering I've seen.
And the last one.
Yeah. So do you know what happens if so it feels like you start from 1, 1, 1, 1, and then you go to R, and then you get like this sort of connectivity swapping. So when you transpose a partition, do you know what happens to the connectivity?
I have no idea, but that's a really good question. Yeah.
Yeah, like it feels like it should like go from high to low and low to high, but I don't know.
Yeah, and maybe that is the right way to think about it. And it just so happens that with low R, it matches the dominance ordering. Like it is possible that something like that happens. I don't know. That is a very good question.
Also, I wanted to know when you said like it fails at 6 because you get a poset instead of totally ordered. Like what changes? Like what does it look like?
So I'm not sure it fails because we don't really understand what's going on with the partitions. Like for 3, we were able to use the partitions because we only have 3, so we were able to use it to study the faces and so on. For higher R, it's not really clear. We have like a bunch of things that we know are faces, but like the thing, like the hard part about this is proving that you don't have more faces, right? That's kind of the hard part. And for 6, what happens? Say that again.
Can you like make a connectivity picture like this?
Oh, so
Vers-
the problem is that, so if you have, so for 3, you have something like 3, 2, 1,
Mhm.
and 1, 1, 1, right? And then what happens is 3 is always like different. The R partition is always different, so you can forget about it. And then the thing is, this is adjacent to this. When you do 4, let's see, 4 would be 4, which you forget about, and then 3, 1, and then 2, 2, and then 2, 1, and then 1, 1, 1, 1. And then the idea is 3, 1 is adjacent to 1, 1, 1. 2, 2 is adjacent to here. And, oh, this is 2, 1, 1, 1. 1, 1, 1 is adjacent to itself. And 2, 1, 1 is also adjacent to itself and to 1, 1, 1, 1. So maybe we should write on the other side. Just here. Because you have a loop here, and then it's adjacent here. So in some sense, the top elements on the dominance ordering for very low R, they are adjacent to everything up to, let's say, the last one. And then when you decrease the dominance ordering by 1, you go up in how far are you adjacent. So like if you did one more, so like 5, you would have 3, 1, sorry, 4, 1. You have many things. And then at the bottom, you have 2, 1, 1, 1. And then 1, 1, 1, 1, 1, and 2, 2, 1, right? Now, I think the 4, 1 is still adjacent here, but then you have 3, 2. And then I think that this is, I would have to check, but I think the 3, 2 is adjacent to 1, 1. And then you go up to that one, you don't go higher. So in some sense, it's like, you're kind of like matching partitions that are high in dominance ordering with partitions that are low in the dominance ordering. And it's kind of like in the interval in between, you have information on adjacencies. But like, we don't really know what's going on. This is like just the patterns that we have for like 2, 3, 4, 5. For 6, things start to break down. But for every picture that we have, like this one, where you draw the edges, you have this sort of like layer thing.
Yeah.
Yeah. But I don't
Okay.
think, okay, I think I just understood your question. Is your question like, how are the layers when it's not
Yeah, how does a
perfectly ordered?
picture change?
I don't know. We don't have a picture of like that
Over
high.
6? No,
Yeah.
that's fair. So that was
Yeah,
cool.
we
Thank
don't
you.
have like a list. Yeah.
Yeah, this is great.
Yeah. Well, maybe let's stop the questions for now. Another round of applause. Thank you so much.